Okay, chapter 12 begins with something called tangent lines. They're fairly simple. Just as a review, tangent to a circle means that a line that's in a plane of a circle, and it just kind of grazes the circle at one point. So it doesn't cut through the circle. That's a different kind of line. That's called secant. We'll talk about that later on. But for today, it just grazes the circle right there at point B in this picture. Now the point where that line touches the circle is called the tangent intersect. It's the point of tangency. Okay, so I know we talked about the SOHCAHTOA tangent. This just means it grazes. It's not the relationship between the two sides, that kind of tangent. So in this example, in this review portion, we'll go back to what we did in chapter 1 and 2, where we talk about how to name a ray. So we have this one right here, ray BA. Remember, the single-headed arrow, it always points to the right, and we would say ray BA is a tangent ray, and that the segment, notice no arrow there, is a tangent segment. So that's all we have to say there. We've talked about the word inscribed before. All that means is if something's inscribed, it means it's inside. That should be simple to remember. And circumscribed is outside. I know it looks like I have a writing of a kindergartner. So the first theorem in chapter 12 just talks about what it means to be a tangent line to a circle and basically what you can get from that. The main thing that you want to get from a tangent line is perpendicular. So the radius is perpendicular to a tangent line. So I'm going to attempt to draw this picture because I couldn't download the notes that had the picture already drawn, so we're going to have to go with my elementary drawings. We have our radius right there. If we were to draw a line tangent to that circle, it would just, barely graze the circle, and it would create a little 90-degree angle right there. So when they have the AB, what they're referring to is if we had a point A right here and a point B right there, and we'll say the point of tangency is P, and we have O as our circle name, the center. That's a P. I'm so sorry for the writing. It's very hard to draw this small with a stylus. So this is saying line AB is perpendicular to line OP. So anytime you have a tangent line that is tangent to a circle, the radius and that line will form a 90-degree angle because they are perpendicular to each other. Hopefully you're going to understand that this you're going to use to figure out what other angles are, because 3 angles of a triangle equal 180. So if you have a 90-degree angle and one other ones, then you can get the third one. So that's what you're going to be looking forward to. Now the next one, this example, this is how we'll use that. See if I can blow this up a little bit. Oh, no, can't do that. If you have ED, which is right here, and you are told that it's tangent, then you can figure out what the third angle is because you know that this is 90, and you already were given that this one's 38, so by triangle angle sum theorem, 180 minus the 90-degree angle minus the 38 will give you 52 degrees. So the main thing from theorem 12.1 is just to remember tangent lines to circles give you 90-degree angles. Alright, and then the other one, BA is tangent to circle O, same exact thing. That's 90, so same thing, 180 minus the 90-degree minus the 22-degree gives us 68 degrees. Now, just as a reminder, you guys, since this is new to everybody, you can always hit pause when you're doing this. You work these out yourself so you can get a feel for it. Don't just, take my word for it, okay? So moving on to theorem 12.2. Oh, and I keep wanting to just move it, and I can't. I have to click. Okay, So 12.2 basically says if a line is in a plane of a circle and it's perpendicular to the radius, then you can call it a tangent. So it's basically the converse of theorem 12.1. It tells you if you have a line by a circle and you form a 90-degree angle, then you have a tangent line. That's all it's saying. I will attempt to draw the circle and do the same type of thing over again. No promises. See if I can blow it up, maybe. A little bit anyway. Alright, I'm getting better. So I have a circle. I have a line tangent to the circle just like before. Hopefully I can just kind of graze the circle. I won't label the AB stuff. We have this radius and we have our 90-degree angle, and we're told that that's 90. So from that we can gather that, I guess I should write A and B. AB is tangent to circle O. And that's basically it for that one. So moving over to the next set. Try and blow this up here. Circle O has a radius of 5. Point P is on the outside of circle O such that segment PO is 12, and point A is on circle O such that segment PA is 13. And they want to know, is P a tangent to circle O at A? Very confusing with the wording. Basically, the main thing you want to get from this is they're asking you, is it tangent? The only way to tell if something's tangent is if it forms a 90-degree angle. So try a process of elimination when you're doing these problems. If you don't know what they're asking or how to do it, then work backwards and think, okay, well, the only thing I know about tangent is it forms 90-degree angle. So you're going to have to work with that somehow. So basically, it's going to be if some angles add up to 90, or if, you know, the triangle angle sum theorem works out, then you know it has to be a right triangle type of deal. So that's where you're going to go with it. You want to know, is this a right triangle? Yes or no. And we did that a couple chapters ago. So I'm going to draw this picture. I'm going to move this over just so we have some room. I'll move it back after. So we have this circle. And we have circle O. Let me draw O. And we are told that P is outside of the circle. So let me just put it here. And we know A is on the circle. Now there's different ways you can go about this. You'd have to use your common sense. You need a triangle, so you don't want some craziness. You know, kind of keep them together. And you know that from P to O is 12. So if I label that, this is 12, and you know that P to A is 13, and you know that if PA is a tangent, then you're going to have 90 degrees, because that's what the theorem says. So if that is true, if this is 90, then these two together, angle P and angle O, would have to equal 90 when you add them together, because it has to go, all three add up to 180, and if this is 90, which means that is a tangent line, then the other two have to have a sum of 90, because 90 plus 90 is 180. So that's the logic that you're trying to work through. So if 12 squared, because that would have to be the hypotenuse if this was a 90-degree angle. We don't know that yet. I'm just drawing it to say if it was. 12 would be the hypotenuse. So 12 squared would have to equal 13 squared plus something. Oh, the other one was 5. The radius was 5. We missed that one. Sorry. Plus 5 squared. So this would have to work out in order for this to be a right triangle. If it doesn't work out, then we know it's not a right triangle. So we get 144 for 12 squared. This is 25, and this is 169. Well, I don't even have to know what 25 and 169 add up to be, because I know that they don't add up to 144. So I know that that is not a right triangle. So not perpendicular, not a right triangle. So you are using your previous knowledge from other chapters. All right. Theorem 12.3 says, if you have two segments that are tangent to a circle from a point outside, then segments AB and CB would be congruent. So a picture to imagine this, I'll blow it up a little bit. You have a circle again. Probably should have made that smaller. And you have point A and point C. And you have point B, we'll call this guy point B out here. If A to B and C and B, if those two are tangent to a circle, then you can say that these guys are the same length. And that's what they're saying. So if two lines are tangent to a circle and they meet at the same point outside of the circle, then the lines are the same length. No ifs, ands, or buts about it. Okay, so let's implement that a little bit. So we have segment QS and QT. They're tangent to circle O, and at points S and T, give a convincing argument that the diagonals of the quadrilateral QSOT are perpendicular. So from Theorem 12.3 that we just talked about, if both of these are tangent to circle O and they both meet outside at point Q, then they are both congruent to each other. And if you have this situation, if you look at, draw the diagonals the best I can, and from here to here, I know that these are both 90 at S and at T. I end up having a kite, okay, because the diagonals are perpendicular. These guys right here, okay, it's definitely not a square, so it's a kite because diagonals are perpendicular. Okay, so that's what, give a convincing argument that the diagonals of the quadrilateral are perpendicular. We can see that it's a kite. We have the radii are congruent, obviously. Adjacent sides congruent, and that's the definition of a kite. So by definition of a kite, the angles are the diagonals are perpendicular. Alright, and last but not least, our example 5. Circle O is inscribed in the quadrilateral. Find the perimeter. Now these ones can be confusing. This one is a basic one. It can get really nasty. You can have this working your way around the circle and have expressions instead of numbers. So it gets confusing in that sense. So just be prepared to put your thinking caps on if you get a more difficult problem. But you're just using the Theorem 12.3 from above. If 2 points are tangent to a circle and they meet at the same point, then they're congruent. So with that being said, RY and SY are the same length. So I know that this is 8. Now moving over to this side, SZ and ZT would also be the same length because they follow that definition as well. So this would be 6. That would make UW7. That would make XU11. Because these guys meet at the same point, so they are congruent. These two are congruent, these two are congruent, and these two are congruent. So from that knowledge, you can go ahead and add them all together and get the perimeter. And instead of adding them all separately, which would be really long, I'm just going to say, since there's 2 of each number, 2 times 8 plus 2 times 6 plus 2 times 7 plus 2 times 11, and if I add up all that, I end up with a perimeter of 64. Remember, perimeter just has a single dimension feet. It's not feet squared because it's not area. So that is what you guys are going to be doing tomorrow during class for the assignment. Fairly basic, not too bad. So hopefully you gain the knowledge out of this. If you have any questions, Edmodo me, If not, I will see you tomorrow.